Hello, everyone. Let's move on to the new unit, Chapter 5, Trigonometric Functions and Graphs. So if I think way back to grade 10 math, we did right triangle trigonometry. So we were just concerned with right triangles, sine, cosine, tangent ratios, and solving for unknown values, right? So these classic basic right triangle trigonometry problems. Then we moved into rotational trigonometry, where we considered negative values of trigonometry. We also talked about sine and cosine law, where we don't have to have right triangles anymore for trigonometry. And now we're coming full circle here, and we're thinking about trigonometry in terms of functions and graphs and connecting them to more complex things in nature other than just right triangles, right? So like wave functions and movements of things like earthquakes and things that scientists study all the time. Music has its basis in trigonometric functions. Okay, so let's go to our first lesson here. Let's explore the graphing of sine and cosine functions. So exploration, graphing y equals. So we are going to do this, folks. We are going to graph y equals sine of x. So let's build on this first by thinking about this. Complete the table of values for the domain 0, or the domain x is between, x is greater than or equal to 0 but less than or equal to 360. Give your answers to 2 decimal places when necessary. Okay, is there any relationship to the unit circle? So y equals sine of x. So if x is 0, so sine of 0 is 0, so y is 0. So I have my coordinates 0 degrees, 0. When x is equal to 30, sine of 30 is 1/2. When x is 60, sine of, let's give exact values. When x is 60, the sine value is square root of 3 over 2. Okay, and so on. So these are values on the unit circle, right? Is there any relationship to the unit circle? Yes, of course. I'll just foretell what's going on. These are exact values on the unit circle. Okay, let's fill the rest of these in. Sine of 90, that's 1. Sine of 120 degrees, that's square root of 3 over 2. Sine of 150 degrees, that's 1/2. Sine of 180, 0. Sine of 210, so we're into the third quadrant. So sine of 210, negative 1/2. Sine of 240, negative square root of 3 over 2. Sine of 270, so our quadrantal angle between quadrant 3 and 4, that is negative 1. Sine of 300, negative square root of 3 over 2. Sine of 330, negative 1/2. And then sine of 360 full circle is 0. So there is our, for a range of values for the domain 0 to 360 degrees, there are the y values for sine. So plot the points on the grid below. Do not join the points yet. Okay? All right, so I'm going to start at, let's see, 0, 0. Okay, and then I have 30 degrees, 1/2. So that is 30 degrees. So each of these tick marks is 30, right? So 30 degrees. 1, 2, 3, 4. So 1/2 is about there. Okay, 60 degrees, square root of 3 over 2. That's roughly right about there. Okay, and then 90 degrees I have 1. And then 120 degrees, square root of 3 over 2. And then at 150 degrees, 1/2. Well, you can see these values, I think they're repeating, right? 180 degrees, I have 0. Okay, let's continue. 210 degrees, I have what? Negative 1/2. So right about there. Okay, 240 degrees, negative square root of 3 over 2. So right about there. 270 degrees, negative 1. And then 300 degrees, negative square root of 3 over 2. 330 degrees, negative 1 half. And 360 degrees at 0. Okay, if I keep repeating this, right, I know that I can keep doing this, right? Our values, like if we do those coterminal angles, we're going to keep getting these values, right? And hopefully you see a pattern establishing here, right? So if I go this way, right, I can use the property of symmetry here. Oops. Right there. Right there. Right there. Right there. Okay. Might see some kind of nice pattern happening, right? So let's continue. Do not join the points yet. Graph y equals sine of x on your calculator using degree mode and the following window format. So go ahead and do that on your calculator, right? So I'll pause here. Okay, make sure you're in degree mode. Okay, folks, you gotta make sure you're in degree mode. Otherwise, this graph's gonna look not so nice. So sine of x. And then check your window. You have to check your window. So negative 360 to 540. And then x scale is 30. Okay, and then the y values, minimum negative 1.2, positive 1.2, and 0.2. Okay. When I graph that, you see a nice smooth curve, and I would use the term, it oscillates. It goes back and forth. There are cycles. So sinusoidal curve, so a sine function, cosine function, looks like a wave. It oscillates. It has cycles. It repeats. On the grid, copy the graph accurately from C to complete the graph of y equals sine of x, negative 360 to 540. Connect the points with a smooth curve. So let's do that. So nice and gentle curve here. I'm going to do an arrow because it means it continues. So let's continue here. Down, 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 up, up, up. Okay, and then end it with an arrow like that because it continues on. Okay, awesome. State the following for the function y equals sine of x, where x is defined on the set of real numbers and is expressed in degrees. Okay, and then the new terms. We have a couple of new terms here. We'll define those in the next page, right? But just stick with me for now, okay? Domain is x such that x is greater than or equal to negative 360, but less than or equal to 540 degrees. X is an element of all real numbers. The range. Well, what's the low and high values? So so if I'm defining the range, sorry, if I'm defining the domain like that, so I'm not going to do open-ended arrows. Okay, folks, sorry about that. Minor little detail, but super important. I have to end the sine function at negative 360 here because that's how I've defined the domain, right? And then positive 540 here. Okay, so sorry about that. No open-ended arrows. Okay, so the range is what's the low and high value? -1 and +1. So it oscillates between those two low and high values. So range is y such that y is greater than or equal to -1, but less than or equal to 1. Y is an element of all real numbers. What's the amplitude? We'll define that on the next page, but the amplitude is the maximum vertical distance that the sinusoidal function varies above and below like a horizontal axis, right? So if I think about the symmetrical horizontal axis, right? So let me just get rid of this and this. Okay, what is that horizontal axis that this sine curve or the sine function varies above? So the maximum vertical distance the graph of a sinusoidal function varies above and below the horizontal central axis of the curve. Central axis, so I'm going to draw a dotted line. And let's do it in what color? Yeah, let's do it in blue. Does it look like that's the central axis? Sure does, right? Because that's where the point of symmetry looks like, right? So I'm going to label that as central axis, right? Horizontal central axis. So it's the maximum vertical distance that it varies above a horizontal central axis. So what is that distance right here? That's the maximum distance. Okay, so is this, right? So the way we look at the amplitude is I take the maximum possible value, I subtract it from the minimum possible value, and I divide by 2. That's the formula for amplitude. And the amplitude is 1. And that makes sense. This value here is 1 unit. Okay, so that's amplitude. Period. Period is, okay, the length of the interval of the domain over which a graph repeats itself, the horizontal length of one cycle on a periodic graph. So start at a point and go through one cycle and then stop at one and stop, and that's one period. So if I do this, right, let's start over here in green, right? I start, here's my up cycle, the positive, right? And I cross the horizontal axis and I do my down cycle. And I get back to the same starting point here on the horizontal axis. And I'd start an up cycle again. So from here to here, what is that period? What is this amount? That's 180 degrees. What is this amount? 180. So this entire cycle, so I'll highlight it here. This entire cycle, right? This entire cycle, it covers a domain of 360 degrees. So the period is 360 degrees. So 360 degrees. X-intercepts. Well, where does it cross the x-axis? Well, it repeatedly crosses. I'll highlight this in blue. Right there, right there, right there, right there. How can I write a general statement for where it crosses the x-axis? Well, I can say 180 degrees times n, right? So if n is 180 degrees, if n is, and I have to define n as an element of all integers, okay? So if 180 times 1, that's 180 degrees, right there, right? What about this one? What if it's 180 degrees times 0? Well, that equals 0 degrees, and that's right there. What if it's 180 degrees times 2? That's 360 degrees. Is that an x-intercept? 360 degrees? Sure is, right there. And you can just keep doing that for all these x-intercepts. Okay, y-intercept. Well, we have a single y-intercept. It's right here. And that's at the origin. Okay, a student was asked to reproduce the graph and be in radian mode. Write down the graphing calculator window format the student should use. Verify your answer by graphing y equals sine of x with this new window setting. So if I'm going from in radian mode, okay, so I need to look at this carefully. Boundaries are negative 360 degrees, which is negative 2 pi. And then it goes all the way to 540 degrees, which is 3 pi. Okay, so that's 2 pi at 360. This is 2 pi plus pi more, and that equals 3 pi at 540. So we stop at 540. That's our domain. Okay, so how do we graph this with a new window setting? First of all, you need to be in radian mode. Okay, your graphing calculator needs to be in radian mode. And then you go to your window settings and input this window setting for the x's, right? So the domain, negative 2 pi, so that's the x minimum, x maximum, 3 pi. And then every 30 degrees, every unit is 30 degrees. So if I just show you here, right? So every tick mark here is 30 degrees. So what is that in terms of radians? Well, that's pi over 6. Okay, so the scale. So this is x min, x max, and this is x scale. Okay? And then the y values. Y values is the same, negative 1.2, 1.2, and 0.2. So for these sinusoidal curves, the sine function, cosine function, you really have to be careful with radians and degrees, because I will ask you to express the functions and the graphs in both degrees and radians. Okay, so you have to be ready for all those conversions. Okay, next page. Okay, terminology. This is where we'll define everything. Periodic function, a function that repeats itself over regular intervals, cycles of its domain. So a sine function. So y equals sine of x. We'll learn about y equals cosine of x, and much later on we'll learn about y equals tangent of x. All of these are periodic functions. They repeat themselves over regular intervals. Just like we saw, it looks like a wave, right? Period. The length of the interval of the domain over which a graph repeats itself, the horizontal length of one cycle on a periodic graph. So on a periodic graph, you could start anywhere. So I'll show you a couple examples. I start here, and then go through one cycle, and then stop, and that's one period. So if I start here, that's the up cycle. I'm at the horizontal axis, and I go back down. This is the down cycle, and I come back up, and I stop. This is my period right here. So I will highlight it right there. And if I read that carefully, that period is 2 pi, right? So if I'm looking, that's 2 pi. Okay, that's one way to do it. I usually start from the horizontal axis, so right here, and I do this up, down, and then I'm back at my starting point. Read that horizontal distance. Okay, that's the period of the graph. Very important characteristic. So if I start here, well, I can start here. I go down this half cycle, this part, and I'm going down come back up, right? But I need to be back where I started, right? One full cycle. Okay, because I got one down cycle here. I have half of an up cycle, half of an up cycle, and I finish here. So this is one full period. Well, what is that? This is pi over 2, and that is a little hard to read. That's 5 pi over 2, which the distance between that is 4 pi over 2, which is 2 pi, which is the same period as before, whether you measure it from here to here or do it in blue. Okay? All right, so you can measure period in a number of different ways. That is one of them. All right, so that's the period of the graph. Let's keep going. Amplitude, the maximum vertical distance the graph of a sinusoidal function varies above and below the horizontal central axis of the curve. So if this is the horizontal central axis of the curve, what is the maximum vertical distance above and below the horizontal central axis of the curve? So above it, this is 1. Below it, it's 1. Okay, so the amplitude is 1. Oops. I'll just put this period in this graph is 2 pi. Okay, sinusoidal curve. So here's the generic term. It's the name given to a curve that fluctuates back and forth like a sine graph. So anything that fluctuates back and forth like a sine graph, that's called a sinusoidal curve. It's a curve that oscillates repeatedly up and down from a center line. So a center line. Here's my center line. Trigonometric functions are sometimes called circular because they are based on the unit circle. So the sine function y equals sine of theta relates to the y coordinate of the point on point P on the unit circle. So right here, if I look at the circle, and if I turn this circle and I roll the circle out like this, it'll form a sine graph, right? Okay, so if I look at this value here, the sine of pi over 2, well, we know that is 1. Okay, sine of pi over 2 is 1. And that's the point 0, 1. Okay, correspondingly, here's pi of 2, pi over 2. So if I say the sine of pi over 2, this corresponds to a y value of 1. Okay, so the coordinate here would be pi over, oops. So the coordinate here would be pi over 2, 1. Okay, which corresponds to sine of pi over 2 is equal to a y value of 1. So that's how the unit circle relates to the sinusoidal function, the sine function. Okay, on a cosine function, y equals cosine of x, y equals cosine of theta, relates the x coordinate of point P on the unit circle. Okay, if I take the same point here, this is still 0, 1, just like before, right? But on a cosine function, if I do the cosine of pi over 2, because we're at pi over 2 on this part right here, right? Pi over 2 equals 0. Well, that is the x coordinate. So this coordinate here is 0, 1, and then that, my friends, here is the x coordinate on the unit circle, translated over to the cosine function. Okay. All right, folks. Visualizing a sinusoidal function, a sine function, then a cosine function, as like I'm taking a sine function, putting it in a Cartesian coordinate graph, so something like read from left to right or right to left. But how does it relate to the unit circle, like we said in the notes, right? So here's a cool little animation from GeoGebra. If I start with the sine function, and here I can trace it out. So you can see when sine is 0, right? Sine is 0. If x is 0 radians, then sine is also 0. So we don't see a trace yet. When we get to about 1/2, right, the sine value. So let's back this up. When I get to pi over 6 radians, the sine value is 1/2, and there it is, right? So I'm just looking at the y values, right? And you can see right here, okay, this is pi over 6 radians, and then the y value itself is about 1/2, okay? If I keep going up, I'm going to reach a maximum. Well, I know that sine of pi over 2 is 1, so I reach a maximum. And I keep going, quadrant 2, I get lower. So my x values are getting lower until I reach the 0 point at pi. So sine of pi is 0. If I keep going, quadrant 3, I'm going to reach a minimum. So the y value keeps going down. I reach a minimum at 3 pi over 2. Then I literally, so when I say come full circle on this sinusoidal function, I literally come full circle at a period of 2 pi. So 2 pi back to where I started from. That's the sine function. Okay, so I'm going to erase the trace. Okay, let's start over, and I'll let the animation go by itself. Okay, so there it goes. So that's the sine function, literally going full circle from a unit circle to Cartesian coordinate system. Okay, so let's stop that animation. Let's bring it back to 0. Let me show you the cosine now. So I'm going to leave the trace on. Cosine. Remember, cosine of theta, or cosine, are your x values. Okay? So right now, cosine of theta, cosine of 0 is 1, and you see my plot starts here at 1. So as soon as I start getting a positive angle, so if I go all the way down to 60 degrees or pi over 3 radians, I know my cosine value is about 1/2. Okay, so there's about 60 degrees right here. Cosine value is about 1/2 on the unit circle. Okay, I keep going. I know that cosine of pi over 2 is 0, so my graph reaches a 0 point. Keep going in quadrant 2. Cosine of pi is -1. I reach my minimum point that's shown on the graph there. I keep going all the way to 3 pi over 2. Cosine of 3 pi over 2 is 0. There's no x value. Okay, or the x value is 0, sorry. Keep going, and I'm going to reach full circle maximum 1 period of rotation. Okay? So let's start over. Erase trace, I'll let the animation go. And there it is. Okay, reaching the minimum point, going back up, x is 0, and reaching the maximum point. Okay, and so on.